All right, hello everyone. I hope you had a nice reading week. Got a little bit of a recharge. I have a bunch of notes. I've been looking ahead of everything coming up in the rest of the semester, and these are the things maybe you should be thinking about at this time. I'll just make a few comments on these. Midterm grades, of course, were a bit on the low side, and a lot of that was from the last problem, which was the where a lot of you struggled on the velocity polygon problem. And I understand that the time was not really long for doing the midterm, and that was probably one source of the issue. I'm not promising anything, but as I mentioned in my message before on the midterm, you may get another chance to show what you know about velocity acceleration polygons on the final exam. And I'll try to make the final exam, of course, it's a long exam, and I'll try to make it less of a time crunch for you, so you can make sure to show me what you know. Regrade requests you need to submit with that form I attached. Check it out, it's on Quarkus as well. If you see any issues with how we graded those, check out the solutions that we posted as well. Projects, this is an important week for your projects with the draft report due. I moved the deadline back one day. I've been getting a lot of questions about how complete the analysis needs to be, and some of the methods, force analysis, and if you're doing anything with gears or cams, we haven't even finished those yet. In addition, if you're doing other analysis, maybe you're still finalizing your designs at this point and whatnot and trying to rush it. So the analysis results in your draft report don't need to be complete. Okay, so make them as complete as you can. And we're not going to be grading you on how accurate or complete your technical analysis is. We'll do that at the final submission. So at this point, include as much as you can. And if you are able to not just leave it blank, but if you can include a draft analysis, at least it should have the objective of what you're studying and why. What are you going to try and answer with dynamic force analysis? What are the assumptions you're making going into that? What are the force analysis components that you're including? Are the weights of the links? Do you think they're important or not? And what kind of conclusion are you going to draw? And can you make that conclusion even if the numbers aren't quite there yet? And maybe that would be a draft conclusion, which you may make your educated guess or hypothesis of what the conclusion is going to be, something like that. As much as you can give, that's going to allow us to give richer feedback to you. Okay, the most important thing to think about for the draft report is building this argument. What's the point of your whole study? Okay, and it's not just here's a new design and look how cool it is. That can be a small part of it, but the biggest thing is you're trying to make a specific recommendation. So we really want you to lay out that, think about it, the whole report is serving, what's your engineering recommendation? And it comes from the client, and a lot of you are doing what the client asked. Some of you are saying, no, what you asked for really doesn't make sense, and here's why. Or here we tried it, and here's the problem with what you asked for, and here's what we suggest, that kind of thing. So as much as you can include, we posted some additional resources of things. Take a look at those that we posted about. One is basically a list of questions you could be asking yourself that your report could try and answer. Any questions about the projects? Yeah. Oh yeah, about the midterm, yeah.
Is there a way to apply the same curve to everyone?
Yeah, I applied a small curve. A number of you got 100% on the exam. So I didn't curve anyone above 100%. So I applied a curve which is not, everyone didn't get raised by an equal number of points. It kind of compressed up a little bit. Yeah. But it wasn't a big curve anyways. Yeah. So that's how I've decided to curve them. Yeah, any questions about projects or the midterm? Okay, and problem set 6 is out on force analysis, static and dynamic. So this week, or today and in the next lecture on Thursday, we're going to finish static analysis. And then starting on Friday and continuing next week, we're going to do dynamic analysis, adding accelerating masses, which I think is really cool. It's a powerful technique, and probably a lot of you will be sort of waiting to apply that for your projects. So check that out. I gave you a liberal deadline, so you have plenty of time to work on that, and we'd be able to give you those graded. Our final exam has been scheduled. It's pretty late. I forget the day, you'll have to check it. It's a pretty late one, so you'll have time to review the force analysis. We will also have some sort of problem set on the next topics of gears and cams. Due to the timing at the end of the semester, probably that'll just be an ungraded problem set. And I'll announce how we'll handle that, if I'll have you submit them or just as practice problems. Last thing is Lab 4, which is about force analysis. And Lab 4 is asking the question, how can we apply what we're doing in class in lectures and problem sets, which are static snapshots of force analysis, studying input-output force of the mechanism in this configuration? Lab 4 asks, how can we do it for a whole motion? Turn the crank and calculate forces. And you'll have to look up when you're doing that. They're starting this week. Yeah?
The problem set 7 is ungraded. Would one of the problem sets from 1 to 6 then be dropped?
Whatever, yeah, the question is about dropping one of them. Whatever number are graded, submitted problem sets, I'm going to drop one of those. Okay. Your lowest one, yeah, as I wrote in the, regardless of how many, yeah.
It does require that they're all submitted though, right? Like someone can't just force it and not submit one of the problem sets.
Yeah, I ask that you submit all of your problem sets to be eligible for dropping one of them. If you're not sure what that means and how it applies to you, if you submitted a petition or something like that, send me a note and I'll clarify for you. Any other questions about anything? Lots going on at the end of the term. Okay, so force analysis. This is what we've been working on. Today we're just going to be doing some work on the board. The next 2 lectures, I have some interesting examples, and we're going to see how we can solve some tricky problems, tricky force analysis problems today and on Thursday. And just as a reminder, static equilibrium. This is the concept we've been looking at, where we assume each link by itself, we can do sum of forces equals 0, sum of moments equals 0. That's our whole concept, static equilibrium. And so for now, we're assuming the mechanism's not moving. Next week, we'll let the mechanism move, and we'll call it dynamic equilibrium. We'll apply the same thing. You remember we had these things, 2-force and 3-force links. We look for those when we can, and they're kind of pre-solved for us. We've pre-solved the method for 2-force and 3-force. Otherwise, we rely on sum of forces and sum of moments equals 0. For each link. And we talked about how forces are transmitted through kinematic pairs. So those are the things we've done so far. And we did 1 or 2 brief examples. Today, we're going to be doing a concept called superposition. Superposition. And this handles cases where we have lots of forces on our mechanism, which makes the more forces or more inputs you add to the mechanism, it's going to ruin all of your 2-force or 3-force links. Because links are going to get loaded up. If all the links have a weight on them, all of a sudden they all transition from 2-force to 3-force, or from 3-force they have 4 forces now, something like that. So we're going to see one great way of handling those, which is practically very useful and simplifies the problem. On Thursday, we're going to do the last static problem, or static method, which is a cool technique called link subsystems, where we're going to draw free body diagrams around more than one link. And we're going to do sum of forces equals 0 on a set of links. Okay, but today, superposition. Superposition. So you've likely encountered this term, and this is what we're going to call linear superposition. Linear superposition. And basically the idea here, I'm going to give you a really simple mechanism, just a lever. We have 2 forces on our lever. F1 and F2. So if F2 has double the moment arm of F1, then F1 is going to have to push harder than F2, right? To be balanced. That's a static equilibrium concept. And you'll notice here I didn't have to plug in numbers. We can write an equation like this. You know, the problems that we've been doing, we've been plugging in numbers. We said the input was 10 newtons, and we calculate an output moment for the mechanism in Newton meters. But in fact, for static equilibrium problems, if you double the input force, so let's say we doubled F1, okay, it's just going to balance with a doubled output force. Right? That means we're going to double the output to stay in equilibrium, right? And then we call this a linear system. So we'd say this system, or static equilibrium problems, static force analysis problems, And it's the input to output relationship. Okay, is linear. Okay, it's a linear, we're going to be able to write a linear relationship. If we double the input, it's going to double the output. Okay, and this is just a factor of, right, there's no nonlinear terms that appear in this kind of problem. Of course, the geometry can be nonlinear. Like if the mechanism moves, all of a sudden we have to do trigonometry to read, it'd be a whole new geometry, and we'd write a new relationship. So this is just for one snapshot in time, this is going to hold. But what this is going to mean is that we're going to be able to consider multiple inputs. And if you solve the problem once, you can know what it's like. If you double the input, you can have the answer immediately. You don't have to resolve the problem. And what we're going to do next is we're going to say, if we have more than one input on a system, how can we divide it into two solutions and solve them independently? Let me give you an example of a nonlinear system just for comparison. A classic nonlinear system, you've looked at some before, I'm sure, is aerodynamics. So let's say we had, here's my awful airfoil. So here's an airfoil, like an airplane wing. And let's say we had air flowing over it here, and it led to some drag. Okay, and drag is going to be some function of velocity, air velocity number 1. And that itself is going to be nonlinear, right? We might have drag proportional to velocity squared of the input, right? So already we have this quadratic relationship. It's not linear. And in fact, aerodynamics is really highly nonlinear. Imagine if we added a second input. Let's say we had a second input as velocity of air from the top going down. We could say drag 1 is due to velocity 1, and drag from 2 would be velocity 2 due to velocity 2. Oops. Right, these are like two separate inputs to this aerodynamic problem. And the question is, can you just add them? A simple way to, or a way to simplify problems is say, okay, let's assume, there we go, velocity 1 and velocity 2. Let's just assume we have one input, one velocity, and let's calculate the drag or measure it. And then let's take that away and apply this airspeed coming in and calculate the drag. Would we be able to just add those two, add these two solutions? For aerodynamics, the answer is no. Right? The result or the mechanism by which drag is generated is very complicated and depends a lot on the geometry here in a nonlinear complicated way, as you'd study in the fluid dynamics course. So the total drag total is not a summation of the individual components. Drag 1 and drag 2. In fact, if you wanted to study that, you'd have to start from scratch and put in a full complex fluid inputs and somehow study those two together. So this is a classic nonlinear system, much more difficult to study, right? And if you want to study two inputs, you have to study them together, and they all influence each other. Static force analysis is much simpler. If we want to put two inputs on our system, we can study those independently and then add up the results at the end. So we're just going to look at these, the implication, and we're going to do a quick example of this for static force analysis. So I'll make the main statement here, superposition. So this is going to, well, the practical way that we're going to use this is what do we do with multiple input forces? And we've studied problems with just one input force and one output force, or it could be a force or a moment. So what do we do if we have multiple? And our result, as I've basically alluded to, is we're going to study each independently. And we know that static force analysis problems are linear with respect to those inputs. The output to input relationship is linear, which is going to allow us to add the result we're going to just be able to calculate them independently and add them up. And we'll do an example of what this looks like. So before reading week, we studied a problem of a slider crank. So I'm going to try and draw it in the same geometry as before, because we're going to use the same input from before reading week, and we're going to just add a second input to this. So this is our slider crank, link 1, 2, 3, and 4. And last time we had this load, it's the input, and this was 1,000 newtons pushing over here. And we had a scaled, I'm kind of acting because I'm doing it on the blackboard here, but we assume that we have a scale diagram, so we know the dimensions and geometry of our link. Of the links, we can measure those. And our goal for the analysis before was, for this input, calculate, if we put a motor here on the base of link 2, how much torque or how much moment does that motor need to exert on link 2 to balance this input? Okay, so M2, how much M2 did we require to balance that 1,000 newtons there? Okay, and we calculated this. I did it approximately on the board. We're going to add a second input to the mechanism, though. That's what we're going to study now. Let's say you did this analysis, but you said, you know, link 3 is actually pretty heavy. I looked at how it's built, and link 3 is quite heavy, and the gravity is pointing this way. Let's say we wanted to include the weight of link 3. So we're going to say link 3 has some weight at its center of mass here. Okay, it has mass M3. And this little symbol I drew here, this is a center of mass symbol. Or you'll see people call that COM, center of mass. So if you're just dealing with weight of a link or something like that, you can just apply its weight at its center of mass, pulling down. We'll see later on links, if we're rotating links dynamically, we're also going to have to worry about how the mass is distributed along the link. Think back to your dynamics, basic dynamics. But if we're just doing a static problem, all we need to worry about is that center of mass. So the weight's pulling down here, M3G. And let's say we know the weight of this and multiply it by 9.8 meters per second, and we get 500 newtons. Okay, so this is basically appears in our static analysis problem as a second input. We have one input, we have two inputs. And so your one option, if you don't use superposition principle, you could try and study this problem. And superposition principle is going to be, it's going to be optional. You can try studying problems without it. I'm going to propose to you that using superposition is going to make it easier, but you can always attack it without. The problem is, let's think of how this affects our problem. Last time, if you remember before reading week, link 4 was a 3/4 link. So let's just consider them both at the same time. Consider M3G and that force P. So let's think of how that affects our links. And the important ones are link 3 and link 4. Okay, link 4 we knew from last time is a 3/4 link with P applied here. There was a normal force pushing up, and there was a force from 3 onto 4. That's what happened last time. Adding the weight doesn't change that. It's going to change the loads. It's going to change the values. But link 4 can stay a 3/4 link. And we were able to solve it pretty readily because we knew that the force from 3 onto 4 was acting along the length of link 3, if you recall back to our solution last time. And that's because link 3 was a 2-force link. So before we added the weight, 2 weeks ago, link 3 appeared as a 2-force link. All of a sudden, we're applying another force to it, so it's no longer 2-force and becomes a 3-force link. Okay, and that makes the problem a lot harder, because now you have 2 3-force links touching each other, and it makes it very difficult to calculate the force between them. And as you're solving some problems going forward, I would encourage you to try solving problems, for example, using this method, or our option 2, which is to use superposition. Okay, and I'll tell you right now, if you try this, we're not going to go through it just for time today, but you could get to the solution ultimately. You can always solve a problem by looking at sum of forces on links and sum of moments on links and setting them equal to 0 individually and solving for a bunch of things. But the difficulty is going to be find F43. F43. We don't know the direction anymore. Previously, last week we knew the direction. This is going to be difficult now, because you have 2 3-force links next to each other. It's really nice when you have a 3-force link next to a 2-force link. Those analyses inform each other. And if you want to remember how that works, check back to our last lecture before the reading week. Okay, so that's one option. You could try that, and I encourage you to give that kind of thing a try. Today I'm going to introduce, or we'll see how it plays out with our option 2. And so I'm going to give you basically an equivalent mechanism, or an equivalent solution practice, a solution approach. So this is our real mechanism. So I'm going to say that equals, I'm going to draw, basically I'm going to divide the problem into 2 now. So the first part of the problem, superposition, we're going to study it just like we did last time. Let me draw that a little clearer. Okay, so this is all we're going to include for the first piece, where M3G equals 0. Or maybe a better way of setting that is set M3G equal to 0. So set one of our inputs equal to 0, and only consider the first input. Okay, and we're going to calculate moment 2 due to the one input, which we'll call P here. So I just put it in parentheses next to it to say that's moment 2 due to P alone. And to that, we already solved that last week. To that, we're going to add on the second input. So now we're going to set the other input, P equal to 0. And we're just going to study how M3G produces a balanced moment. Okay, so we're going to calculate 2 moments. One moment is due to P, one moment is due to the weight of link 3. And then our total output, our principle of superposition now, this is the step of superposition, is just adding those. So we're going to say M2 total equals the 2 of these added up. M2 due to P plus M2 due to the weight of link 3. Okay, linearly add them up. And we know that applies because it's always going to work for these static equilibrium problems or snapshot force analysis problems. Any questions about our method? So we're going to solve this, and we're going to look at the numbers and make sure we add these correctly, because sometimes it actually gets a little tricky to add them properly. We'll keep track of our signs and whatnot. This is the one we haven't solved. So this is going to be step 1. We already solved it. And step 2 over here. If anyone could look up, I have in my notes a solution from this one, but it's a little different than I solved it live in class. If anyone could look back, I'll ask you in a little bit if anyone can remember this one from last week, 2 weeks ago. We'll come back to that in a minute. Okay, step 2, let's solve this one. let's solve this one. So this is just, it's going to be a similar process, a little different than solving M2 due to P. Okay, moment 2 due to the weight. So like always, a force analysis problem, we start with some free body diagrams. If you're not drawing free body diagrams, you're really doing yourself a disservice because it's the only way to really reliably look at force problems. And it doesn't take long, so you need to do it. Okay, so this is our link 4. Link 4. Next, we'll put the forces on in a second. Next, let's get the angle a little bit better. I'm drawing link 3. Okay, and the final one over here is going to be link 2. Okay, I'm going to put some points on here. We call these points B and D. I'll put those up on my main diagram. Okay, so these are our three links. And we did this for M2 due to P before. So things are a little bit different now. So here we don't have our P anymore on link 4. But we will have a normal force. And that's like F from 1 onto 4. Normal force there. And we know it's up, but we don't necessarily know where it is. The other force we're going to have on link 4 is some force from link 3 onto link 4. From 3 onto 4. And last time we showed that it was right along the length of link 3, and we knew the direction right at the beginning of the problem. Now we don't know that. We don't know that. We need to look at link 3 first. Okay, so that one, we know it's there. It's applied at D, but we don't know its direction or magnitude. So let's move on to link 3. Okay, so we're going to have the same interaction from 4 onto 3. F4,3 is equal and opposite to F3,4. So that's where these two links touch each other. We also have F2 acting on link 3 at B. We don't know anything about those, but the new force we have is the weight. Okay, it's down 500 newtons. So that's all we know from this one. Okay, so last time we were able to study link 3 and 4 by themselves, and we were able to solve those. So let's see if we can do that now. Link 4 is a two-force link, right? There's only two forces, and there's no moments. So link 4, last week it was three-force link, now it's two-force link. That's great. Two-force links, really easy. The two forces are equal, opposite, and collinear. So all of a sudden we know F1,4 needs to be up, so F3,4 needs to oppose it. There's just two forces, equal, opposite, and collinear, and they both have to act at D. We knew F3,4 acted at D, so the normal force also needs to go right through there. So link 4 is basically solved. Two-force link, that's great. So we can take this F3,4 and we can put it on here. It's also vertical. And its magnitude is the same as F1,4, which we don't know, but we know its direction here. Okay, so these are the forces on link 3. Is this a three-force link? There are three forces. So we ask, is there any moments applied? It's a pretty easy check. We just have forces, so no moments applied. So link 3 is now a three-force link. Link 3 is a three-force link. So these we know how to study, although this one's a little bit unique. And the unique thing about this, we haven't seen this yet, is that the two forces we have already are parallel, right? And you'll recall the process for solving these three-force links is that all three forces need to point and intersect at a common location. We call it a point K. So where's K on this one, if they're parallel? Any ideas? Where would these two parallel lines meet? at infinity, right? It's kind of like instant center. We had a similar kind of thing, right? Sometimes for Kennedy's theorem, some things would be off at infinity. Is it up or down? It doesn't matter. Yeah, I agree. It's just they could meet at either infinity, up or down, right? So it's just a direction, really. So we'll say k is at infinity, or it's just kind of an abstract concept now, and it's really just a direction. So it's vertical. So what that means is that our third force, over here F23, also needs to point at infinity. So it also should be vertical. You probably could have guessed that, right? To be balanced, this link, these two forces don't have any horizontal component. So clearly this force shouldn't have a horizontal component either. So it should also be vertical, right? And we'd have to guess whether it should be up or down. Although as you're solving problems, you'll probably realize that a lot of times you can guess it right off the bat. I'm just going to guess down. Okay, three forces. We know its direction now, but we don't know the magnitudes. We don't know the magnitudes. So force polygon, right? That's the technique for three force polygons, for three force links. Okay, because they're parallel, though, a force polygon is not going to work. All right, here's my force polygon. M3G is down. Okay, and the other two forces are along this line. Right? It doesn't lead to a polygon. It's just a line now. So having all three forces aligned, our three-force link paradigm or solution method kind of breaks down. But the good news is, actually, this one's pretty easy to study. The direction was pretty easy to find, and now the magnitude, well, we'll just find it using another method, right? Force polygon, it doesn't help us. It doesn't help us. But we can find the unknown force by another method. When in doubt, if everything's breaking down, resort to sum of forces and sum of moments. So you can choose which to use. Sum of forces isn't going to help us here. There's no horizontal forces. In vertical forces, we have two unknowns. Two unknowns. So that one's not going to be able to find our answer. But moments is usually, moments is a little bit more versatile for solving. So let's try and use sum of moments to solve for the unknown F23. Okay, and the reason that sum of moments equals 0 is versatile is that you can choose the point about which you sum the moments. So ultimately, we don't really care about F43 because we're trying to calculate stuff on the left side, M2. So our goal should be to calculate F23. So if you want to do a sum of moments equation that only solves for one unknown and eliminates the other one, let's be clever and choose sum of moments about D. Right? That's going to eliminate F43 because F43 goes through D. F43 goes through D. So F43 doesn't appear in this. And this is why sum of moments is maybe the most powerful. Whenever we have two unknowns, think about doing sum of moments. Okay, so sum of moments about D, we need a direction for positive. So the standard I like to use, counterclockwise is positive. That's what we did last time. You could define the other direction, but just be consistent. Okay, we have sum of moments about D. M3G, the weight, is going to be multiplied by some moment arm. I'll call it D M3G. Okay, so it needs to be like this. The distance from D to our force, it's a perpendicular distance. So that dotted line there, that's D M3G. That's the moment arm of M3G about point D. Okay, and the sign, let's check if it should be positive or negative. It's down, right? So think if this was like a pivot here at D. Is that force, that weight, is it causing a counterclockwise or a clockwise moment? It's pulling down. So it's creating a counterclockwise moment. We said that's positive. So good. That one's positive. And now the other force is F23. And that's going to be multiplied by its moment arm. And that's going to be just the distance all the way over. I'll draw it up here. All right, so the moment arm of F23 with respect to D. So that's this perpendicular distance there. Okay, we need to ask ourselves, is the sign here positive or negative? The way I drew it, it's down. It's down, right? So that's also going to create a positive moment. And this is where we're going to find out if that was correct. I guessed that one. I guessed that. So we're going to see if it's correct now. We just solved for the unknown. F23 is our weight, m3g, times the ratio of those two distances. Okay, so we had 500 newtons for the weight. And those lengths, based on roughly how I drew it last week, we know that the weight is halfway across, right? It's at the geometric center, I said. That's the assumption we made. So this ratio should come out to 1/2. I'm looking for the numbers I used roughly last time, so I can give you a reasonable number here. Yeah, 5 centimeters and 10 centimeters for this length and the total width, dF23. Okay, so we just end up with half the force, 250 newtons. Any questions about this one? Yeah. Oh, yeah, I totally forgot about the sign. Thank you. I said we're going to find out whether it should be positive or negative. You say, oh, we're missing a negative sign. Yeah, we're missing a negative sign here. So the answer we get is negative. And whenever you get a negative force, you have two options. You can just leave it as negative, or you can say, oh, this one was wrong, right? You can just flip it and change the sign. So that's an option if you want. I find that a little bit more logical to do a little bit of a draft solution and then come back and change the direction. Then we would get a minus sign and a plus sign. And dealing with positive forces and positive moments is usually a little less ambiguous. Okay, so positive in the upward direction. And that makes sense. If you look at this link being balanced, right, we have up on the right. We need to have up on the left to keep it balanced. Otherwise, it's going to spin, right? So probably you can just look at the link and guess that correctly in the future. If you don't want to guess, or if you don't want to infer it a little bit, you can go through the process and see whether it's positive or negative. Any other questions about this? Great. So our last step, we've done link 4, link 3. Now we just put that onto link 2. Put it onto link 2. And now this looks just like last week's, 2 weeks ago, problem. Here's link 2 with O2 and B. F23 is vertical. So F32 should be equal and opposite, pointing down. We know there's a force here from the ground onto this link. That's at the base pivot. And we have this moment 2 due to the weight. Okay, so this is just the same as before now. It's not a 2-force link. It's not a 3-force link. But we do moments about O2. And we get F32 times its offset distance here. And that's positive because it creates a counterclockwise moment. And the moment that I drew, M2, is also, I drew it as counterclockwise. So that should be positive in my equation as well. So this is our moment equation for link 2. So you just need to measure D32 and you can calculate the moment. And it's going to come out to be negative, which means that the way I drew it was incorrect. So the numbers here, we have 250 newtons And this distance should, it's going to be a pretty small one. I measured it out to be 3 centimeters from the drawing last time. So M2, due to the weight, is 750 newtons times centimeters. That's M2 due to the weight. Any questions about that before we add it to, that's solution 2, before we add it to solution 1? Did anyone have a chance to look up, oh yeah.
Oh, so you just said that you basically guessed the wrong way for M2 should be the other in your drawing?
Yeah, negative, sorry. Thanks.
That's okay.
I keep talking about keeping track of our signs and then I'm forgetting them. Thanks for reminding me. Yeah. Did anyone have a chance to look up M2 due to P from 2 weeks ago? I can use an approximate one.
120 Newton.
Say it again?
120 Newton meters.
120 Newton meters.
Yeah, clockwise.
Newton meters. Clockwise. So clockwise, and this is where we need to just keep track of things, right? We kind of converted it to positive. This one, we want to add these two together, right? That's our M2 total. We need to add these two results together. So we just need to make sure we're keeping track of our positives and negatives. So this one we said was positive clockwise. And let's just convert our units here as well, right? 120 Newton meters. So this is Newton centimeters. So what do? We divide by 100, right? 7.5. Yeah, it's pretty small, isn't it? Okay, but it's negative, right? And negative, we said negative moments are clockwise. So both of these, 1 and 2, were clockwise. Okay, so you can keep track of it manually, or maybe a more systematic way would be to keep the signs. So I said negative means clockwise. So let's remove those and just keep the signs and keep our standard. So this is a case where we just, maybe the best way to keep track systematically is keep the sign, and we just add these up and we get negative 127 Newton meters, and the negative sign means clockwise. Okay, so that's our final answer. And at that point, you could decide again, do you want to report it as a negative number or a positive number? So just be very clear. If you want to write a negative number, you need to write what that means. M2 total, I've just run out of board space. So I'll give you some maybe 2 ways that we could show this result. M2 total equals, what do we come up with, 127.5. Okay, the first option is to give it as a positive number. Or if you want to write it as a negative number, if you want to write it as a negative number, you need to be much more explicit about what that means. It's hard to say, if I wrote negative 127 clockwise, does that mean it's negative clockwise? Negative and counterclockwise. Does that mean negative counterclockwise equals clockwise? Right, this is ambiguous here. Okay, so that one isn't good. So I could write negative, and then I could write in parentheses a little statement that interprets that. Negative means that our result is clockwise. Negative means clockwise. Okay, so I think this one is clear. I think that one, most people would see that and agree. And positive is always going to be clear. Okay, so those are 3 options. The middle one, I'd say, is no good. Great, so we've solved the problem. As a little summary here, we divided this problem with multiple inputs into 2 simpler problems. And we solved them independently, and we added the result. Okay, and that always will be an option whenever you have multiple inputs. Whether or not this process is faster than just trying to solve it in one step with both forces, that depends on the details of how hard this one is. And we didn't do this option 1. You could try that out. I'm not guaranteeing that superposition is going to be always faster, but I think logically it allows us to resort to and use our simpler relationships, 2-force and 3-force links. Okay? It's going to allow you to use those, which I think is a better way of solving problems with fewer mistakes. It also allows you to draw an additional conclusion. We can see that the weight was much less of an influence than the P force, right? The P force. And it turned out to be a significant less, which I'm a little bit skeptical of here. I'll have to check that afterwards to see what we did, if we made a mistake there. But if this is right, the conclusion here is that maybe the weight, you could almost ignore it. It's 100 times less or 50 times less. You could consider it ignoring it maybe. So doing this superposition allows you to see the relative strengths of those input forces. Great, that's all for today. Next time, link subsystems.